We're going to work with two main methods for dealing with electrical systems called Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law involves looking at each junction in our system and realizing that the total current into any junction has to be equal to zero. That means that electrons cannot be destroyed or created. They can only go from one place to another. The whole procedure will break down into 4 steps. First, we define any voltages or currents of interest. Then we sum the currents into any junction. Then we apply any element laws. And then we combine any equations to eliminate unwanted variables. Before we do our example, let's first recall what the element laws are. So we have 3 main elements: resistor, capacitor, inductor. And then I've written the element laws here relating current to voltage drop using the S notation. In other words, I equals C times S means C times the time derivative of the quantity V1 minus V2. So let's do this first example with a resistor and a capacitor. We start by defining voltages and currents of interest. First, we have the voltage at the junction here, which is just going to be equal to VO because of the definition of the voltage across the capacitor. Similarly, we have IR and IC, which are the currents going through the resistor and the capacitor. If we sum the currents going into that junction, that's just going to give us IR minus IC equals 0. It's no surprise that the current going through the resistor has to be equal to the current going through the capacitor. If we apply the element laws, we have 1 over R is equal, IR is equal to 1 over R times E minus VO, and the current going through the capacitor is C times S times the voltage drop across the capacitor, which is VO minus 0. Since these two are equal, we just set them equal to each other, and we get this, which can be simplified into C times V dot plus 1 over R times V is equal to 1 over R times E. So there's the differential equation with input E and output VO.